So today I would like to discuss situations where the string move in a non-trivial space-time. So there are two sort of aspects to this. The first has to do with the effect of the local curvature of space-time on the motion of the strings. And the second has to do with the global topology of space-time. They both have interesting effects. I'm going to sort of separate the discussion by first discussing what happens if I on a flat space, on a small deformation of a flat space-time. And later on in the lecture, I will discuss a situation where my space-time is flat but not trivial topologically, meaning that some directions of space have been compactified to circles. So the theory on the worksheet now is the theory of maps from the worksheet to the space-time. Theories like these are called sigma models, quantum field theories of this sort. In dimension higher than 2, sigma models with curved target are never renormalizable. Because when you write an action like this, and you expand out the metric into powers of x, then in dimension higher than 2, x is dimensionful. This part by itself already has the correct dimension for a marginal operator. And so all the corrections to that are irrelevant. So nonlinear sigma models do happen. They are very interesting, but they are always effective descriptions of some other quantum field theory in the UV. For example, you can use a nonlinear sigma model to describe mesons to some degree, to the pions. But the pions is not a theory, is not a UV complete theory for the pions. Now, in 2 dimensions, the situation is different because the field X is dimensionless. And so when you expand out the metric into powers of X, you will find an infinite collection of terms which are marginal. Then you do quantum mechanical calculations with Feynman diagrams, you renormalize the theory, and these marginal couplings will run in general, logarithmically. So when you study your theory, you'll end up with a metric which is actually a function of the scale. There is energy flow. And in particular, the theory stops being scale invariant. If it's not scale invariant, it's surely not Wall invariant either. So unless the beta function cancels, this cannot be a good starting point for a string theory because the Wall mode does not decouple. So in order to understand if you can use an action like this to describe a string, you need to understand the beta function of the metric. So you need to compute something like mu de mu. The indices are terrible. We call them nu and rho. Okay. And you get some beta function, which is going to be a function of the couplings themselves. So you can sort of see that requiring the beta function to vanish might potentially give you some equations of motion for the background metric. Because I get a constraint, some function of the metric equals to 0. The function has 2 indices. And this is true for every other coupling you can write down. I was mentioning yesterday the possibility of writing a coupling that looks like this. For example. If I do that, then I'll get modified beta functions, beta function equations, and I'll get a beta function equation for B. Sorry if the beta and B are a bit similar. This is the function, beta function for G. This is the beta function for B. So now that I introduce a new coupling, I get a set of coupled equations for the metric and for this B field. So this is equal to 0 and this is equal to 0. Now, how would you actually compute these beta functions? Well, I can sort of briefly explain to you how would you set up a perturbation theory for a sigma model, for a nonlinear sigma model. So intuitively, whenever you have a path integral, so you're trying to make sense of a path integral of this sort. So if you try to evaluate perturbatively, what you're doing is that you first identify what are the classical solutions. For example, an example of classical solution could be my fields are constant and sit at some point in the manifold, for example. So you integrate over the classical solutions. And then you study the small fluctuations around the classical solutions. By just expanding this in the power series in the legs and doing your result Feynman diagrams. Now, in order to have an expansion parameter at all, it's useful to it's useful to sort of put something in front of our, some formal parameter in front of our action. So that, and consider a target such that the curvature of the space-time is small in units of this alpha prime. So that you're studying small fluctuations around flat space. So that allows you to write things like G mu nu equal delta mu nu plus something small. So sorry, what I'm trying to say is that once you introduce a normalization like this, you can convince yourself that as you expand out this in powers of delta x, all the interactions will be weighted by powers of alpha prime. Anyway, so this perturbative expansion is valid when the curvature of your space-time is small in an appropriate sense. So when you expand out the metric, anyway, if you, I can't say. So the beta function for the metric at the leading order looks like this. This is actually quite a straightforward calculation. You use, if you want to do it in detail, you use something called Riemann normal coordinates, where the metric is written as something flat plus something quadratic in the position, whose coefficient is the Riemann tensor at that point. So now you have a quartic coupling, or the sort of del X, XX. I just write on the simplest Feynman diagram for the one loop Feynman diagram for the quartic coupling, get a contraction of two indices, and the Riemann tensor becomes the Ricci tensor. So this is one loop, a one loop calculation on the worksheet. And so you see that the leading order, the equations of motion for the metric, is that the metric is Ricci flat. So you find Einstein equations. As you add more fields and more couplings, the equations the beta function gets modified. And it starts looking like the Einstein equations in the presence of matter. And these fields get reasonable equations of motion as well. Now, are there any questions about this?
That's just an analysis on the worldsheet.
Yes.
It doesn't mean that in the 26 dimensions, the field G mu and that coupling is going to be like that, right?
What do you mean with the field G mu?
I'm talking about the theory in 26 dimensions, the metric, the Einstein fields. Well, we know that it's non-renormalizable in like a field theory without thinking about the worldsheet. So when you do this analysis, it is just like the embedding.
So for now, we have sort of two different notions of metric, right? There is the G mu I put there in the action describes the motion of the string, and it's just a background, the classical background I put there, and I find that this classical background has to satisfy the equations of motion, Einstein gravity. And then there is separately this other notion where I look at the string modes, and at low energy I see that string theory behaves like a quantum field theory, and I find gravitons. So now I would like to explain how these two notions are related. But you're right, at this moment they look completely separate. Right? I had these gravitons with their own scattering amplitudes of themselves and other particles, and I have these background fields. So what's the relation between them? Let me observe something. Suppose I expand the metric that I was saying around flat space. So what happens to the action? I get the usual action, right? Plus a correction. So do you remember what was the vertex operator that we insert for a graviton? It was something that depended on how did it look like?
X du, del X du.
Right, let me go in complex coordinates too. That's right. So we have del x mu, del bar x nu, epsilon mu nu of p e to the I p x p dot x, correct? And do you notice any resemblance between these two? this is just the Fourier transform of that. So suppose that I asked you this question in quantum field theory. Suppose you know how to solve, to compute Feynman diagrams, random perturbation theory, for, I don't know, QED, for an electron scattering off photons. What would you do to describe the motion of an electron in a classical electromagnetic background? How would you describe a classical electromagnetic background? That's right. So concretely, I have my electron, right? I do my standard Feynman diagrams, but I add some external legs, right? Where I put my classical source. I mean, I'm trying to treat the source perturbatively. Does this even make sense? Another to think about this is that the classical background can be written as a coherent state of photons. So sort of exponentiate the photon creation operator, and I act on the vacuum. So let's try to do the same thing in string theory. So now I'm going to have a sphere. I'm going to have some local operators which describe external particles. And then I need to insert a lot of gravitons. So I'm going to take my graviton vertex, right? And I'm going to insert it at a lot of locations. And with, I mean, I only did the exercise for the 4-point function, but you can easily convince yourself that even for n-point functions, at least at 3 level, the effect of the B ghost is just to cancel out the C ghost for all the operators, for all the points I use as moduli. So if I have a sphere with n punctures, I can use the position of n minus 3 points as moduli. And the corresponding B field just cancel out the strip of the C's. So all I need to do is to integrate this V of G everywhere. So and some, right? So I'll have sums of correlation functions where I have my original vertex operators, and then I have the integral of the graviton on the whole surface to the power of n. Correct? But this is the same as just writing down the actual exponential. But if I do that in the path integral, this just means that I'm adding this to the actions on the worksheet. So I'm doing precisely this. So if I treat perturbatively a small fluctuation of this background, it will reproduce, it will be compatible with scattering amplitudes of gravitons. So this supports the idea that somehow the equations of motion that I get by setting the beta functions to 0 will be the same as the equations, the classical equations of motion for the fields associated to the string modes, to the low-lying string modes. Notice that I put the graviton vertex operator here, but I could have done this for the vertex operator of any string mode. these vertex operators always satisfy L0 equal to L0 bar equal to 1. So they have scaling dimension 1 plus 1 equal to 2. So they always look like marginal deformations of your action. So the collection of string modes is really in one-to-one correspondence with the collection of possible deformations of my worksheet action, marginal deformation worksheet action. So this sort of tells you that even bosonic string theory doesn't really have continuous parameters, because all the deformations, all the continuous deformations of your action can be identified with actual dynamical fields, particles in your theory. Now, there is a coupling which is a little bit messy, but because it's hard to see when your worksheet curvature is flat when you go to the flat gauge. But it still matters, because after all, your worksheet is not globally flat. It's really a counter term that appears when you do calculations. And so there is another coupling which is interesting, which looks like this, proportional to the Ricci curvature on the worksheet, and that's a function of x. So I was telling you that it's a little bit hard to disentangle, it's a bit messy to disentangle the graviton vertex operator from the dilaton vertex operator. So I wrote something like this, and then I told you the traceless part is the graviton and the trace part is the dilaton. This is roughly true. There is a bit, when you try to actually write down the Q closed representative, you get some extra terms involved in derivatives of the ghosts. It is really a bit messy, but not very illuminating. But the final claim that you find in Polchinski textbooks is that the deformation that corresponds to the dilaton is something like this. Now, this is, again, we could discuss for a while what is this issue. For example, when I say that this is the metric, even this statement is debatable, in the sense that this is the metric felt by the strings, almost by definition, but it's not the metric which satisfies Einstein equations on the nose. So there is something called the Einstein metric, which is some power of some exponential of the dilaton times this metric. So in writing down the equations of motion or comparing beta functions with scattering amplitudes, there is a little bit of freedom in redefining your fields. And in particular, whenever you have a scalar field, like the dilaton, you can redefine the metric by just multiplying by a function of dilaton. So let me just sweep all these details under the rug for now, actually, for this string, for this course at all. But let me just leave it at this. So let me ask you, what happens if this phi is constant? This gives me the integral of the curvature. The integral of the curvature on the worksheet counts essentially the number of handles of the worksheet. So the effect of this term when phi is constant is that my original perturbation series for string theory where this was genus Z, where this was no handles, one handle, two handles, and so on the surface, gets weighted by extra powers of by something like e to the 2 phi. So changing the background value of this dilaton ends up shifting the coupling. So even the coupling is not a continuous parameter, but is a dynamical field. Okay. Right. Now, there is one fun fact that I said these are the equations of motion. Right? So typically, equations of motion follow from an action. It's not obvious a priori that the beta functions could be written as the variation of an action with respect to something. But it's actually a true fact about beta functions in two-dimensional quantum field theories. So you can write some effective action with a property that the variation of the space-time action with respect to some field is the beta function for the field. So let me just write down the action restricted to the massless fields of the theory. So when I say square here, I mean contracted with a metric. So here, see, this is what I said what I meant when I said that the metric X, metric G, is not exactly what you would call the Einstein metric. The action contains a power of the dilaton in front. It's a very natural thing to write down the action like this because, after all, the dilaton is essentially the coupling. So this is sort of telling you that the action has a 1 over the string square in front. Right? In this normalization, all the fields are normalized in such a way that the strength of the interaction is G string. When you do a redefinition like this, then you can go to a more standard action where you have just the Ricci curvature, the Ricci scalar, and in front you have something like the Planck constant. Anyway. So, okay, it's a reasonable action for the metric, a B field, and an exascalar field. So comparing the Einstein metric and the string metric, you can get the statements like the one I was mentioning, perhaps at the very beginning of the lectures, that string theory has 2 scales. One is the string scale set by alpha prime, once you put alpha prime in your action, the on-shell conditions for the string modes become something like this. Sorry. So you see that alpha prime sets the scale of the mass of the massive modes. So there is this mass, the scale, the string length that tells you what the energy scale at which the massive string modes become important. And then there is this other scale which is there in every theory of gravity, which is the Planck scale. The ratio between these two scales is the string coupling. So when you compare this action with the Einstein action, you can verify this fact. So the strings are weakly coupled in a regime where the string scale is much, much smaller than the Planck scale. So string perturbation theory is a good perturbation theory where the problems of gravity, in a sense, are cured much earlier than the Planck scale by transforming a theory of gravity and a few fields into something which is completely different, a theory of strings. On the other hand, when the string coupling is strong, it means that the string scale is close to the Planck scale. So, no, okay.
And what happens there?
Well, perturbation theory or string theory is not going to help you at all.
And then
the bosonic string is ill-defined because it has a tachyon. If you study superstrings, the behavior of the theory when the coupling becomes strong can be gleaned from these sort of supersymmetric protected quantities. And sometimes you get just the duality, where when this coupling is strong, some new degrees of freedom come down, which sort of replace the original strings, but give you a new string theory. And sometimes you get something completely different, like M theory. So, right, so in what's called type 2B string theory, for example, sort of you have your string scale, you have the Planck scale, and then there is a kind of a D-brane scale. And as you try to push this up, this comes down. And so you never, and some new degrees of freedom which also look like strings, but are not the original strings, replace the original strings. In type 2A string theory, instead, when the string coupling goes up, a new direction in space-time opens up. You end up with M theory in one dimension high, which is sort of a theory in one dimension higher, which has no coupling, and then there is only the Planck scale. And there is no good perturbation theory, which would allow you to study the behavior of the theory near the Planck scale. Anyway, I wanted to discuss today also the other extreme, where your space-time can have small structures. So here we are doing a perturbative expansion around flat space, where all the features of the metric, the curvature of the metric, was on scales much larger than the string scale. I would like to now examine an opposite situation where the space-time has features at the string scale. But I want to avoid having a non-trivial metric because I don't know how to do calculations with a non-trivial metric at the end. So, and there is a natural way to do that, which is to take space-time and compactify one of the space directions into a circle. So I want to take maps on the worksheet into rd minus 1, comma d minus 2, comma 1 times S1. Now, we already know how to deal with maps into flat space. So all I need to do now is to teach you how to do the theory which describes maps on the worksheet into a circle. The action for this, let me call this coordinate y just to distinguish from the other axis. The action for y is still the same. The action, the stress tensor, and so on, they all look the same as what we had for the x's. The only difference is that y is periodic. So I want to identify y goes to y plus 2 pi r w, where w is an integer. So when I study the theory of y on a cylinder, and I try to do quantization, I first need to ask myself what are sort of the time-independent classical solutions for y. So when I expand in modes, y, I get something like this. So before I could have a mode in x proportional to tau, but I could not have a mode proportional to sigma, to the solved equations of motion, because as sigma goes to sigma plus 2 pi, my field had to be periodic, and so I couldn't have a real contribution proportional to sigma. But now it's possible, because as sigma goes to sigma plus 2 pi, my field goes to the field plus 2 pi rw, like this. So I can consider configurations where the field has a winding, where as I go around the worksheet, the space-time coordinate goes around the circle. Essentially, what this means is that this describes a state where the string might be wrapped around the circle w times. So w is called the winding number of the string. It counts how many times the string winds around the circle. Now, my spectrum now will be built from using the usual oscillators, but starting from states which are labeled by both a momentum and a winding. Furthermore, the momentum has to be quantized because it's dual to a coordinate which is valued in a circle. So actually, the momentum is written as n over r. So I should really label my state by two integers. Then the Kaluza-Klein momentum, so the momentum around the circle, and the winding. And now the L0 and L0 bar eigenvalues look like this. So something interesting happens, that these ground states don't have the same eigenvalues of L0 and L0 bar anymore. You can verify this statement just by computing the expression of del y and del bar y. So, okay, you can compute the spectrum now. The interesting thing is that, so when you have a quantum field theory and you put it on a space-time which has a circle, what happens? Suppose I take a scalar field and I put it on a spacetime which has a circle. So the momentum along the circle gets quantized, right? So now my modes are labeled by continuous momentum in the remaining spacetime and by discrete index, right? My momentum conservation, my on-shell condition now become the momentum in the other directions plus n over r squared plus m squared equal to 0. So essentially what happens is that my field gets decomposed into an infinite tower of closed-Klein modes whose mass grows as a function of the momentum in internal direction. So a scalar field, when I compactify it on a circle, gives me an infinite tower of scalar fields. If it was a massless scalar field, the first element of the tower is still massless, all the other ones are massive. If you do Kaluza-Klein reduction of more complicated fields, you get more interesting answers. For example, the original Kaluza-Klein reduction was about compactifying gravity on a circle. You compactify gravity on a circle, you get gravity in one dimension lower, you get a gauge field, and you get a scalar field, and an infinite tower of massive modes. So where the gauge field and the scalar massless and the massless scalar have to do with how the metric on so the mixed components of the metric and the radius of the circle. But in string theory, the story is more interesting because you don't just get quantization of momentum, you also get these completely new winding modes. So the mass of the winding modes will be proportional to the radius squared, instead of going like 1 over the radius squared. Because the on-shell condition of these modes is controlled by L0 and L0 bar. So you get this picture that you put the string theory on a very large circle, you have a fine tower of Kaluza-Klein modes, and then you have winding modes at very high mass. As the circle size goes down, the Kaluza-Klein mode's mass goes up, but the winding mode's mass goes down. If your circle becomes very, very small compared to the string scale, now you have this very fine tower of winding modes of masses which are very close to 0, while the Kaluza-Klein modes are gone. And now it turns out that there is a beautiful symmetry. I can take this field, I can take the modes of this field, and build a completely new field. But the only difference at the level of the oscillators is that I change the sign with which the anti-holomorphic oscillators appear. So that, and I exchange the role of positional momentum. And I replace the zero mode dual to position, to the momentum, with the zero mode dual to the winding. In particular, del y is identified with del y tilde, but del bar y is identified with minus del bar y tilde. So this operation is called Tduality. If you stare at this enough, you realize that if this was the radius of the circle y, this field has now a radius which is 2 over the original radius. So there is a statement which is not about string theory, it's about two-dimensional quantum conformal field theory. A free boson of radius r is identical to a free boson of radius 2 over r. And this has a string theory consequence. The winding modes that are coming down as the circle becomes small behave exactly as the Kaluza-Klein modes of a large circle. So we took string theory in 26. So if you have quantum field theory in d dimensions, so you put it on a circle and make the circle small, the quantum field theory effectively becomes a quantum field theory 1 dimension lower, because the Kaluza-Klein modes are infinitely massive. But if you take it would have been paradoxical if the same was true for string theory, because string theory has to live in 26 dimensions, bosonic strings. So if I compactify it on a circle and I could make the direction go away by making the circle very small, I would end up with a string theory in 25 dimensions. That's not reasonable. Instead, what happens is that the degrees of freedom get completely remixed, and I land on a new string theory in 26 dimensions. Mm-hmm.
Why is it unreasonable that you would lose 1 dimension if you compactify 1 dimension of the target space? Like, does that just tell you you can't compactify 1 dimension of the target space?
Well, if the direction is very large, I don't see anything wrong with the string theory. Right? If string theory at large distances behaves like a quantum field theory and a theory of gravity, there is no obvious problem in putting a theory of gravity on a target which has a big circle. And at least perturbatively, I don't see any problems where the radius becomes smaller and smaller. The perturbation theory still seems to be well defined. But it would be curious if the endpoint of making the radius smaller and smaller was a string theory in 25 dimensions, because that shouldn't exist. And so the way that the problem is solved is that the winding modes appear and cure the problem. Make a new direction of space-time appear. And this is a very simple perturbative example of a more general theme that when you look at superstring theories, which don't have tokens, are better defined, and you try to push them in directions where they could potentially break down, there always seems to be some extra degree of freedom which cure the problem. So here we could cure a small circle because our strings could wrap the circle and give us winding modes. In superstring theory, you could ask questions about, I put the theory in a manifold which has a small sphere, and then I send the size of the sphere to 0. Will the theory break down? And in that situation, maybe the theory will be saved by d-branes wrapping the circle, wrapping that sphere. I mean, a string could not wrap the sphere, it would just slip off. But a 2-dimensional or 3-dimensional object can wrap a 2-dimensional sphere or a 3-dimensional sphere. So if you do your perturbative string theory calculation on a theory which has a small sphere, you will find some logarithmic divergences. But they just take the form of the effective. So they look like the effective action of a theory where you have integrated away some massless modes, or some modes that are becoming very light. So those were the d-branes wrapping that sphere. Okay, so there are non-perturbative versions of this sort of perturbative self-consistency requirement, that the theory will not break down by manipulating your space-time. But in general, these sort of cures of potential singularities involve heavy reorganizations of the degrees of freedom. And so one typical way you discover dualities, which are relations between different looking theories, is that you push one of the theories towards some finite limit, and you discover that in that limit, it becomes the other theory in a more reasonable limit. So here there is a self-duality of bosonic string on a circle. Bosonic string on a circle of this radius is dual to a bosonic string on a circle of this radius. and the funny limit of this radius becoming small becomes the reasonable limit of this radius becoming large. So what else can I say? Another observation which is worth making is that our computational abilities are really limited by our understanding of two-dimensional conformal field theory. So here I can do calculations because this is a free field. Here, even if I had received by some miracle a metric which satisfies, for which the beta function vanishes at all order in perturbation theory, I still have a very hard time doing calculations because it's an interacting theory on the worksheet. So at the level of perturbation theory and string theory, your ability to understand things is often limited by your ability to understand your two-dimensional conformal field theory. See, in principle, okay. Another observation is that although we tried doing things here with geometry in mind, you don't have to. So here I try to describe a string moving in a non-trivial geometry. And here I did it too, using a conformal field theory, which is maps from the surface into a circle. But there are a lot of conformal field theories in two dimensions. A lot of those are not sigma models, but nothing prevents you from using them in your perturbative string theory. So suppose that somebody gives me a CFT with central charge equal to D, some integer. I could take a worksheet theory described by the CFT times maps from sigma into R 26, 25 minus D, comma 1. This worksheet theory is perfectly fine for defining a perturbative bosonic string. Nothing will go wrong. The total stress tensor will have charge, central charge 26 plus the ghosts equal to 0. This is a while invariant theory. I can combine it with ghosts. I can write down scattering amplitudes. No problem at all. So the space of possible perturbative backgrounds for the bosonic string is very large. Right? It's controlled by the two-dimensional CFTs. If you ask how such a theory would look like, or suppose that this is a nice CFT with a discrete spectrum, right? So the Hilbert space of this CFT will consist of a collection of states. A vacuum, then some state with some dimensions h1, h1 bar, some other state with dimension h2, h2 bar, etc. Some discrete spectrum, which might be very hard to compute, but exists. And then on top of this, you will get Virasoro descendants. So something like L minus 2 of the CFT, acting on the vacuum, and so on and so forth. And I can try to build BRST closed. Mm-hmm.
So now we no longer interpret these operators as coordinates of a worksheet.
That's right. So the string spectrum will now consist of things to the form H, comma, H bar, tensor with some number of oscillators acting on a momentum mode in the remaining directions, tensor with the Gauss ground state. You have a variety of constraints that you need to impose. In particular, you have conditions on L0 and L0 bar that tells you that P squared is I mean, let me do for simplicity something where h is equal to h bar. You might find that p squared has to be equal to minus 2h plus minus some integer. That depends on the number of oscillators. So this means that essentially I'm getting a tower of particles whose masses are controlled by the conformal dimensions, by the scaling dimensions of these for L0 eigenvectors, eigenvalues of the CFT. So this is sort of analogous to the Closure-Klein reduction, but it's not geometric. I'm going to get, the string theory looks like at low energy a quantum field theory on this remaining space-time with some complicated spectrum of fields that depends on the CFT. So when I said that the string theory lives in 26 dimensions, you see that this is a half-truth at best. You can find perturbative vacua which do look like string theory living in any dimension smaller than 26, but increasingly complicated towers of states. So the space of perturbative vacua for bosonic string is very large. And they might look like things moving in any number of dimensions below 26. They all have tachyons, unfortunately, because all CFTs that behave well have a state of 0 eigenvector, eigenvalue for 0. Yes?
You had said before that for the full theory, you would have to consider all possible deformations.
Mm-hmm.
So does that mean that since we can always do a deformation like this, in the full theory we would have like to do the dynamics, and see the dimension dynamically from that? Would it even make sense to speak of a dimension?
If this CFT has continuous parameters, they'll become fields. It's possible that the CFT will be continuously connected to flat space, to a sigma model in R to the 26 minus D. In which case, this will be connected even classically to a flat space. Like just sort of this will be some kind of a non-geometric limit of a compactification in a sense. It's not clear that you can have. I don't know. I don't think much is known about this overall structure of the space of CFTs. I think typically CFTs tend to have no marginal coupling, so no continuous deformation. So I think a lot of these vacua will be not classically connected to each other. But you can try to ask about dynamical ways to connect them. For example, I might wonder if there is some other CFT of central charge D+1, which kind of looks like a sigma model into R times one CFT. So you can sort of try to fiber CFTs on a sigma model onto R. So you can try to have configurations where you have a space-time, but this non-geometric compactification is different in two different regions of space-time, and there is some kind of a wave that sweeps across space-time and changes compactification. You can try to do a variety of things. Yes?
Sorry, what exactly do you mean when you say sigma model?
Sigma model is a CFT defined in the V as maps from the curve into a manifold, where the fields are maps from the curve into a manifold.
So string theory is an example. Bosonic string theory.
The worksheet theory of the bosonic string is an example of sigma model into R26.
Okay.
You can use sigma models in more general spacetimes, or you can have things that are not sigma models. Now, everything here is discussed in the bosonic string, so there are tachyons. If you just take any of these theories and you observe it for a little bit, what's going to happen is that the tachyon is going to decay and the theory is going to become something else. In superstring, you can still consider this sort of perturbative vacuum. And this is what led people some people to believe that string theory might have a landscape of vacuum, a very, very large set of different looking perturbative vacuum. But the non-perturbative phenomena that might bring you from vacuum to another, from a perturbative vacuum to another, are very poorly understood. So even in superstring, it's not clear which of these configurations would be a true vacuum. But at least in perturbation theory, this tells you that theories of quantum gravity are a dime a dozen. So if your only concern is with perturbative aspects of quantum gravity, you can easily build theories with a large variety of theories where different types of towers of fields cure the perturbative problems of gravity at some scale below the Planck scale. The non-perturbative problems of quantum gravity are a different matter. But it's still an annoying. Well, I don't know if it's annoying. It's still a lesson that is a bit harsh. Right? You might have wondered maybe just trying to write down a nice perturbation theory for gravity in some other fields will be enough to fix a theory, a microscopic theory of everything. This is not. This sort of tells you this is not going to be the case. Okay, any questions?